All right, we are recording, and hopefully, sorry, this is the second time I tried recording this video because first time I started thinking about the numbers involved and they weren't making much sense, so I had to do a little bit more looking to have it make a little bit more sense. I'll get to that. I'll still talk about it. But it is definitely a, huh? Anyway, but yeah, I haven't done one of these for a while. It is a, nope, over here, because the description should be over there. Let's make a spaceship. But really, I'm continuing the Manufacturing Materials sub-series of videos because I saw something interesting this week talking about a specific, more or less theoretical, it's more, well, it's less theoretical than more, but process by which new elements are elements in general are made. So yeah, let's get to that. Where is it? There it is. So yeah, this is from Berkeley Lab. Stars forge elements in a way we're only beginning to understand. Unfortunately, this is a Q&A. It is still interesting, but it's just a Q&A. It's not like giving a more technical breakdown of what's going on here. But basically, there are two, broadly speaking, this is me talking, not it. Broadly speaking, there are two ways of making new elements. Okay. One is just direct nuclear fusion, like what's currently going on in the sun. So in the core of the sun, at the moment, because it's still main sequence, you've got hydrogen atom. Except they're not far apart like this, they're actually like that. And eventually they end up bouncing off of each other. Well, very likely bouncing off of each other, but eventually they will collide with each other and do so with enough force. And they're so close together, there's so much pressure pushing them together that instead of being like this, they go like that. They fuse together to create helium. Because hydrogen has one proton each, one proton per atom. Helium has two. When you fuse together, it's the number of protons that determine the specific element. So two hydrogen come together, you get helium. And then eventually, I don't know if there is already some helium fusion going on in the core of the sun. I can believe in like once every trillion or so interactions, maybe. I don't know. It didn't bother looking at that, but it's, eventually though, it's going to run out of hydrogen, or at least it's going to drop below the level that it's usable for fusion, which will cause the pressure to increase because gravity is going to start pulling stuff down into the core, and that's going to cause helium to have to start fusing together, and then we'll get to beryllium, I believe it is. Eventually it'll go up to carbon. Carbon, I'm pretty sure, is where they figure most main sequence stars will stop. Excuse me. So white dwarfs, which are the remaining core from a main sequence star after it's exhausted its fuel, they're basically big hunks of carbon that are glowing white because they're so hot and going to take billions of years to cool off. Anyway, so that's one way that you make elements, but that only gets you up until about carbon, right? So to go higher than that, you need to see a supernova or another process. So supernova can, again, be direct nuclear fusion. So much energy just forces it all together. But that's a single, very high energy event. Everything, once you get past carbon, it seems like it's likely going to be high energy events. Eventually, though, you're going to hit what are called the S and R processes. There's the S process for slow and R for rapid. That these, instead of being direct nuclear fusion, they are actually neutron capture processes. So you got that proton there, right? Well, the protons in the nucleus are rarely alone. Hydrogen is an exception. It typically is just one proton there, and an electron going around. We don't need to worry about the electron. Fairly often you have at least one neutron there. Deuterium would be one proton, is isotope of hydrogen, one proton, one neutron. And it's pretty stable. There's also tritium that has two neutrons. It is not stable, but it does exist. And yeah, as you go to other elements, you do have isotopes where same number of protons, but different number of neutrons. And that can influence their stability. As a hydrogen and deuterium, I'm pretty sure those are both just considered stable. Tritium, it varies. It is unstable, so I shouldn't say it varies, but it does decay over time. Well, when you get to really heavy elements, they can have a lot more neutrons. And what can happen with the SNR process in the correct environment, and this, looking into the environment is where I was like, hang on, I got to look more at this because what the heck's going on here? You can have a very neutron-rich environment such that that atom with so many protons just starts having way too many neutrons. It would be highly unstable, which leaves the atom one of two choices. It can either split off and just lose a bunch of neutrons, just go away and, hey, then it's fine. Or it can undergo neutron decay. And what happens with neutron decay is, I'm pretty sure that's the right term, is the neutron itself, which is about the same size as a proton. It's a little different. It doesn't have a charge to speak of. I'll get to that. Protons do. Protons are positively charged. Neutrons, we treat them as being neutral, hence the name. It can decide, you know what? I'm going to become a proton, and it'll emit an electron. There's more going on than that, but it'll emit an electron, because you have to conserve charge, and makes it a proton. So now, I don't know how exactly I want to do that, but now that a neutron becomes a proton. So you've now changed the element. Okay, that's what's going on with neutron decay. There is more involved because neutrons and protons are both made of subnucleonic particles called quarks. There's also gluons in there. I don't think they factor into this, but there's quarks in there, and it's actually a quark has to change in order to convert from a neutron to a proton, but you still got the electron emission, blah, 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 blah. Nuclear science is very interesting, but it is something I've not really I'm not too studied on, because even then I graduated from college over 10 years ago. But anyway, the S process and the R process, slow and rapid, are two different ways to see an atom eventually undergo that neutron decay. The S process, or slow neutron capture process, come on. You have still, it's a relatively high, well, for free neutrons, and this is kind of important. You got a lot of them there. Tens of millions to hundreds of billions of neutrons per cubic centimeter. Okay, and that over thousands of years, the atoms, enough neutrons build up, and some of them decay down to being protons, so you get a new element. And as it says there, this gets you to about where bismuth is. And I actually have this set up. Periodic table. Pointing the wrong way, and actually bismuth is right there, Bi. That's lead right next to it. And this actually doesn't surprise me too much that they are next to each other. Because lead tends to be like the heaviest stable element. Not to say bismuth is unstable. In fact, there are some that are more stable, that are still stable above lead. But like even colloquially, you think about uranium decaying down into lead, that, when it gets to lead, it's safe. That there's no more radiation there. There are isotopes of lead. Move away from that. But yeah, it doesn't surprise me, though, that bismuth would be next to lead there, and that's what we're talking about, because even if it is a yes, this is the most common thing that, the different decays bring you down to here. Yeah, but we can also be over here. Uranium and plutonium are kind of like that as well. It even mentions lower down. The R process is what will produce uranium, as well as plutonium. When I was looking into nucleosynthesis for another one of these videos, however long ago now, I didn't know this, that plutonium very likely is also produced along with uranium. And so we have uranium on Earth. It's very possible that plutonium as well was part of the gas, dust, and etc. that coalesced to form the Earth. The thing is, for why we don't find plutonium, natural plutonium, is twofold. One is, it may have been an isotope that was unstable and just didn't survive until today. Or, and this actually makes more sense overall, is plutonium is chemically very stable. It's more stable than uranium is. So uranium, it gets over here, it's exposed to all these other chemicals, it ends up binding with some of them. So what we find for uranium ore, it's not pure uranium, it's a compound. It's bound with some other chemical, some other element. I don't remember what, I think I had seen at one point. But that compound is of lower density. It's lighter, so it floats up to the top of the mantle. And that's why then it can be found in the crust. And potentially you can have a volcanic eruption spew stuff onto the surface, or just through normal plate tectonics, you can see uranium ore brought up to where it's accessible to us. But plutonium doesn't react, so it'd largely be pure plutonium would just sink down through the mantle, even reaching down to the core. So yeah, it's one of those things where, yeah, bismuth might make perfect sense, but maybe lead is just got something else going to that everything focuses to that, like uranium is what we actually find, plutonium is what is uncommon. Anyhow, so that's the slow process. The R process, rapid, takes appreciably more than the S process, 10 to the 21 neutrons per cubic centimeter. And that is a much higher density for what we're talking about here. And it also can happen within a second. And this is what makes the actinides, which if I turn that back on, that's this second row. So if you go all the way, my camera doesn't extend that far. If you go all the way over there, well, actually, here, let me. That's lanthanum, that's actinium. So lanthanides, actinides. There. Yeah, for those that didn't know, you can use a browser window, a browser source in OBS to just show a PDF. That's what this is. So, yeah, and also you can't exactly see it down there that well. Education.jlab.org, I think it is. Hang on. Yeah. Jefferson Lab used to have a great periodic table. It looks like they decided to drop that. I can't imagine why. It was great, but anyway. This is still where I still got this from them, though. So yeah, in order to get any of these elements down here, and uranium is... Oh, here, let me... There's uranium. There we go. Then we got... You know what? I'm just going to do it this way. Oh, it won't... Oh, that's right. Yeah. Hang on. There we go. Yeah, so you got uranium over there, neptunium, and then plutonium. Yeah, okay. And give me this one back. Okay. There. I'm not that professional at this. Sometimes I'm just winging it, but I have fun. So yeah, in order to get the enough neutrons there for the neutron decay to work to give us such heavy elements, because you have to have a lot of neutrons there and a lot of neutron decay to get to something so heavy that you get the 90s of protons in there. That's a lot, and there's I think there are hundreds of neutrons. You know, I tried looking up, but I can't because I want to find Jefferson Lab. It had that information. It doesn't anymore because that periodic table definitely doesn't show that, which is a shame. Anyway, so yeah, and what this is talking about here with, I also just realized I forgot to mention certain things at the start of this. I can go back and do that. The intermediate process, or I process, is thought to occur at neutron densities between those two and on timescales between the R and the S process. Technically, it's theoretical, it sounded like from this. Unfortunately, it is a Q&A with this. Does it say that I would assume he has a PhD, so Dr. Matthias Wedekind. I'm not certain on that, but he is certainly one of the researchers and experimental physicists at the Department of Energy's Lawrence Berkeley National Laboratory, or Berkeley Lab. And he's focused on that research. Unfortunately, I say unfortunately, this is just a Q&A with him, as opposed to, hey, we've made this discovery, here's a technical press release explaining everything that's going on here. But this is talking about, we may see that coming in the future. Because we can better figure out the I process, that is another means by which we might be able to produce new elements or just new isotopes even of existing elements. And those can be useful for many things. Yes, there's things such as nuclear power and nuclear weapons, but also nuclear isotopes, medical isotopes, that if we can manufacture those more easily within laboratories, as opposed to some of them are actually produced in nuclear power plants, which reminds me of something from years ago. After Fukushima, Canada, in this one person's infinite wisdom, and by that I mean absence of it, decided to shut down one of their nuclear power plants. Because, Canada is so susceptible to earthquakes and tsunamis. Anyway, decided to shut that down, and it created a global panic, such that I think it was within 2 weeks they turned it back on, because it's the primary source of medical isotopes for the planet. Yeah, that was... Anyway, so yeah, having this other process by which to make elements and isotopes could actually be incredibly important. But it talks about here that the mechanism was first proposed in 1977, been almost forgotten, but now what's being mentioned here is we have telescopes that are actually making observations of various stars and such, and finding anomalies that it's like, well, wait a minute, there shouldn't be elements this heavy here. You wouldn't have had enough neutrons for the R process to produce those elements. So, sorry, I should be facing this way. So that can't be right. There has to be something in the middle, because the gas process isn't going to make those. So there's got to be something in the middle that explains it. The I process, the intermediate process. Just seeing some more stuff here. What does it actually say? Yeah, the Berkeley Lab's 88-inch cyclotron. Now heavy elements form. So yeah, the link to this Q&A is in the description, and I do suggest you look at it to learn more. And it is interesting. I do wish it were more so the just technical document of, hey, we've made this discovery, or hey, here's research that we're doing. Let's explain how it's going in a more technical manner. Because when I was looking at this paragraph, it was like, wait a minute, let me look something up here. And it's like, made me really scratch my head, so I had to look a little bit more. Because 10 to the 21 neutrons per cubic centimeters. For neutrons, sure, for free neutrons, that's impressive. For neutrons in general, no. I was looking up, what is the atomic density of normal matter? It's higher than that. Meaning that technically, like when I looked it up, for water, you have about 3.3 times 10 to the 22, so an order of magnitude more atoms per cubic centimeter. The hydrogen in atoms is unlikely to have neutrons. But the oxygen would. And I'm pretty sure oxygen, its atomic number is 8. There's 8 protons. I'm pretty sure that its most stable form is with 8 neutrons. So we'd have about 2 orders of magnitude more neutrons, a higher neutron density in water than in the either supernovas that are producing the neutron density for the R process, or the collision of neutron stars for the R process, because that's actually one of the places that the R process can occur. You've got 2 neutron stars, and they just collide against each other, or at least go like that, and there's so much energy, so much pressure, that these just seas of neutrons are able to interact, come together, and you get the neutron decay that produces new elements there. I already talked about neutron decay, didn't I? Pretty sure I did. Yes, I did. Goes a little bit far afield. Have to make sure I come back. So, okay, well, how does that make any sense then? How can that work? That it's like you're currently seeing a higher neutron density in me than in what we're talking about here. It's free neutrons versus bound neutrons is the critical difference here. So all the neutrons in my body, they're bound in the nuclei of the atoms. So they can't interact with each other. They're quite separate from each other. And they're also not going to be moving around much relative. Well, they're not going to be moving around much relative to each other. So it's not like, oh, neutron in this atom can decide to do that and something bad can happen. No, it won't, because you've got the larger atoms themselves with the electrons there that they might be bound together, but they're only bound together like that. Okay, at most, they're bound together like that for a covalent bond. They might actually not even be that. It might be an ionic bond. Okay, but it's just that. And it's like over here is where you're actually going to have the neutrons. So they're not going to see each other. But when you're talking about a neutron star, you're basically talking about a sea of pure neutrons. There's probably also some protons there. Actually, now I'm wondering. I would think so. Because I wouldn't think that you would have the R process occurring where it's just a bunch of neutrons together and deciding to change into protons. And like starting at hydrogen, working your way up. That wouldn't make much sense. Because then you wouldn't need a neutron star collision. It would just happen in a neutron star. So yeah, it must be that there's also protons there. I don't feel like looking up what the actual mix is for a neutron star of protons to neutrons, but it's not unreasonable to me that there would actually be protons in there as well. Anyway. I hate when I go off on those tangents and I completely lose track of where I was. That's right, the free neutrons. So the free neutrons, even though technically lower density than what you see in my body right now, it's still, they're actually able to bounce around. They're actually able to interact with each other. So even though it is a technically lower density, the effectiveness of these neutrons, if you will, well, it actually exists. The effectiveness of the neutrons in the atoms of my body would be zero. They're not going to interact with each other. They're not going to be able to go through this process of merging together to form some isotope that's unstable, and then neutron decay changes neutron into proton, new element. That's not going to happen here because they're not able to interact. They're not free to do so. So that does make sense. But yeah, it still is just wild to think about that technically the density is lower than my own body. That is wild to think about. Now that is as far as just particle density goes. And is also the whole it's moving around and such. Because even when I was looking it up, here, let me just check. I need to go back to this. That for a neutron star, you can have neutron-dense materials like neutron stars have incredibly high densities. A neutron star can be 10 to the 39 to 10 to the 40 neutrons per cubic centimeter, which would be 10 to the 12 or 10 to the 13th grams per cubic centimeter. And here, just give me one moment. I'm just showing my crop down, but my browser window here. So this is why I was asking the question. I even do point out I'm confused now because isn't that a lower density? But it does explain this. I like using Duck AI, part because it's free, but it's also get a selection of models. I like using this one just because it's one of the open source models, and why not be open source? I do ask for clarification there, and it explains then, well, those are bound and not free. But it still is. It's like incredibly heavy. So, incredibly dense there. So then why is it that the R process would involve a lower density than what this is saying you can just find for neutron stars? Could just be that the density of neutron stars are variable, and that at the surface, which is where you have a chance of any of the elements being made to escape, is below the level that you need for the R process or the S process. Or maybe it is that you just need something like a neutron star collision to cast the stuff off. But yeah, so looking here, free neutrons versus bound neutrons. Yeah, free neutrons, which is kind of necessary there. Yeah, and also, okay, yeah. Seed nucleus, so that would be what I was talking about, that there would have to be some protons there, you'd think. Yeah. But yeah, it does make some sense. It does make some sense. It's just the availability, the access there. But yeah, so that's a lot more than you may have expected when starting when I started talking about this. But still, I mean, regardless, it is interesting. Nucleosynthesis is fascinating, regardless of the process. Let me scroll down a little bit so we can see more of that image. It's really fascinating, and I like talking about it. I like looking into it because, like I point out in some of the previous videos, we shouldn't be violating the periodic table of elements in science fiction. Like, we shouldn't just say, like, in Star Trek, tritanium. And I looked that up. It's like, tritanium. The name itself, I think, oh, that's an alloy of titanium. No, I looked it up. It's supposedly a new element. It's like, we're kind of running out of those. And, I mean, unless we're talking about the island of stability, which we're not even completely certain is real, it should be. But we haven't found any elements that exist in there yet, so you're talking about building a ship out of a material that would radioactively decay over time. That's a problem. And in Stargate, you've got naquadah, naquadria is an isotope of naquadah, but also trinium. Naquadria and trinium are both at times described as new elements. Both would likely have to be radioactive, though, which again is a problem, especially for trinium. That it's trinium and naquadria are both used for constructing spaceships. So great, you could have radioactive decay occur, and now suddenly you've lost a bulkhead. I mean, that also just makes it interesting as far as the idea of like warfare, that you could just use something that would trigger or encourage nuclear decay, and suddenly a ship will just decompose. It's kind of wild to think that. Anyway, but it's also the idea of naquadah being used to build a Stargate kind of doesn't make sense because, wait, naquadah is radioactive. These things, the canon, according to SG-1 at least, is that the Stargates have been on worlds for about 2 million years. How that means that you've had millions of years of naquadah decaying into another element, and yet somehow these still work. That's pop. And I get the whole, plausible, no, not plausible deniability, suspension of disbelief, that's it. I get suspension of disbelief, I do. But still is a, why don't we just not? Why don't we just try to make sure when we're writing stories, it's an alloy. So it's working with materials that are stable. They're not going to lead to those weird, awkward issues. We're not just doing something that's like a blatant violation of physics and chemistry that, even a high schooler is going to catch. All right, even some middle schoolers might be able to catch that. It's like, let's try to do better than that. And there's plenty of interesting alloys and other compounds that would be fascinating to explore. That or just the possibilities there are so fascinating that why not just say that it's, I'm making up some jargon term for this thing and it's just that. It's great. Moving on. Plus, there's also the aspect of an alloy in theory can be made and it would work, whereas tritanium might never be a thing. As much as I love Star Trek, that might be one thing about Star Trek that will never happen because, no, if we even find elements that do exist in the island of stability, the amount of them would be very low, and they might not have properties that would make them suitable for tritanium. But if we figure out an alloy of titanium that gives us those properties, hey, now we can do it. Because that's part of the fun of science fiction, is what is possible, exploring the concepts of what is possible. And also, just setting those rules and sticking by the rules and trying to use the rules that are near to reality. At least in my opinion, I think that makes them best. Alright, not always. It's all kind of wishy-washy, but I like having rules, and the closer they are to reality, I think that helps with it being approachable, helps it being understandable, and helps overcoming the challenges that are presented by those rules, helps overcoming them be more interesting because it's what more people are familiar with today. Alright, that is certainly plenty of my rambling. I believe I already said it, but I don't quite remember because, as I mentioned earlier, this is the second time I'm recording it. Link to this article is in the description. Go ahead and have a look at it. It is interesting. I have not looked at all of it. I guess I'll just add this. That, final question and answer. How do you see the field evolving over the next 5 to 10 years? What do you hope researchers will accomplish in that time? I think in that time we can really nail down the eye process. There are tons of data sets currently being analyzed to try to figure this out, but it's still, in 5 to 10 years, this guy, this research physicist, hang on, I just want to make sure I've got I'm going to screw up his name if I try again, so it's just experimental physicist at Berkeley Lab. He does believe that in 5 to 10 years we may be able to nail it down and really have a good sense of what this is, and that's going to be quite interesting, especially if we can figure out how to apply it locally so that we can come up with new isotopes in labs more easily than we would otherwise. So, yeah, all right. It's been an interesting one, at least to me, even if I have been stumbling having to search things up. All right. See you next time.